So, okay. So, welcome everyone to today's plenary talks. We're going to have lightning talks from 5 great TAs. We'll see Juanky, Sadhika, Chi-Ning, me, and then Jess. And for each talk, there'll be somewhere less than 8-ish minutes with about a 4-minute section for questions afterwards. So that's like the rough format we'll go for. And if we'll try to keep things on schedule. But without further ado, I want to just let Juanky kick things off. So go ahead.
Thanks. Thank you so much, Cody. So yeah, I guess I'll just give a short talk about, I guess, one of the things that I've worked on in grad school. So this is something I've worked on together with my advisor, Moritz Hart, as well as some other students at Berkeley. And so anyway, I guess to motivate the work, one thing to start off by noting is that typically when we think about machine learning is all about sort of finding patterns in data, right? Like a typical machine learning task is that we collect data, and then try to fit a function to that data so that that function is like predictive on new data drawn from some distribution. So to, I guess, make things a little bit more concrete, I think one of the big successes of machine learning in recent years has been like image recognition, for example. And the way these image recognition tasks work is that practitioners collect a data set of images, such as ImageNet, like say pictures of cats and dogs, and then people go through the work of labeling each one. And then you train a model that will hopefully, pick up on some patterns in the data and make predictions on new images, right? So like when we do self-driving or sort of classify things in like Google Photos, you present an image to the classifier and the classifier just like tells you what the label or content of that image is. And an important assumption in this typical exercise in machine learning is that we assume that our predictions don't affect the nature of things, right? Like if we see a picture of a dog, the fact that we predict that it's a dog or if it's like a house plant or whatever else doesn't actually change what the picture is, what the picture captures. But this is not actually the case for a lot of machine learning applications in social systems, in societal settings. So as an example, you can think about the case of predicting credit defaults for people asking for a loan, right? So a typical example, say like, stylized workflow for how a bank might take in applicants and decide whether to give loans or not is that a bank might collect individual data from people, such as their income, their credit history, whether they've defaulted on certain loans in the past. And based off this data, they'll generate some machine learning classifier, some predictive model that'll say like, hey, for this person, what's the probability that they'll pay me back if I give them a loan, right? So I give out some prediction probability, some default probability, and based off this predicted probability, the bank assigns an interest rate, right? So if the bank's machine learning classifier says, hey, this person is high risk, they're likely to default, the bank will assign a high interest rate to that person. But the thing that happens here is that we have this strong feedback loop, right? So we have predicted a high default probability. The bank in turn gives a high interest rate to the person. And that high interest rate makes it harder for the person to pay me back the loan, pay the bank back, right? So we have this like interesting phenomenon that the predictions that we make are not independent of the outcomes that we observe, but rather our predictions influence the data that we observe, the data here being whether someone will pay back their loan or not, right? So this kind of violates or breaks one of the standard assumptions in machine learning that our predictions are kind of like independent of the things that we're predicting on. So this is kind of like the motivating observation that led to us thinking about, so hey, how do we like formalize these questions? What does it mean to make accurate predictions or good predictions in settings where our predictions really like change the things that we're predicting on, right? Accuracy isn't like as easy to define as it is otherwise. So yeah, so I guess maybe the bird's eye view of formative prediction is that it's like this formal framework to study settings where predictive models are used as the basis for decision making, and these decisions then lead to actions that might change the distributions that we observe. And we call these like model-induced distribution shifts performative effects. And contrary to like supervised learning. So when by supervised learning, I mean the setting that tries to capture, say, like the image recognition example from earlier. In performative prediction, each classifier induces like a potentially different distribution over data sets, right? So like a particular credit scoring model leads to a particular, to a specific, say, distribution over whether people will pay back a loan or not, right? And in general, we want to study these kinds of feedback loops where we use data to generate predictive models. These models influence decision making, and these decisions then change the state of the world, which then generates our data again. So this is at some level related to the kinds of things that Aisha was talking about yesterday in her talk. Anyway, I feel like I'm out of time, or almost out of time. So I guess the point I wanted to make is that, once we sort of understand or recognize these feedback loops, we start to see them in a lot of different places. So like election forecasting, like 538 has a model that predicts whether someone will win the election. But you can imagine that if the model says that a candidate's going to win by a lot, then that might discourage voters from actually showing up to vote because they're like, oh, my vote doesn't matter, right? So then you might have like this self-negating effect where people stay at home. Similarly, like when we predict the state of the climate 100 years from now, that is used to influence policy decisions we make today, and that changes what the environment will look like much later. Similarly, like traffic predictions, when we predict when Google Maps gives us an ETA as to like it'll take 15 minutes to get from your house to work, and that ETA is low, a lot of people might now pick this route, and then traffic gets worse on that route, and then actually the ETA is longer than what Google Maps predicted. So anyway, I guess Cody, I'm basically out of time, right?
You still have like 2 minutes.
Okay, anyway, so just to give a sense of, this has all been kind of like high level. So like what is the theory that happens here? The theory that happens is that we create a model to sort of study these settings where predictive models change the distributions. And the kinds of things that we can prove is that a typical way by which someone might try to solve these performative effects, say like Google and their like ETA routings, that they deploy a model, they see that the model changes the observed distribution because it changes traffic patterns in a city. And then as a result of this distribution shift, people just like retrain. So a question we might ask is, when does this process of retraining ever converge to a limit? Like, will Google always have to retrain every day? Or will it at some point kind of converge to something, and then those predictions will be stable? And using like ideas from the optimization lecture, we can show that if our loss is nice, and by nice we mean like smooth and strongly convex, so the Hessian has these like lower bounded eigenvalues and upper bounded eigenvalues, and that our classifiers don't change the distribution too much, so the observed distribution isn't too sensitive, then retraining, so like this process of like deploying and retraining on new data, will converge to a solution that's like close to the best that one can hope for. Anyway, this is like a bit of a whirlwind. It's not that much time, but hopefully this gives like at a high level a taste for the problem. So I'm happy to take any questions if people have some.
I have a question.
Yeah.
So is this result very similar to like the transference learning results? Because you're like retraining, and that just reminds me like immediately of like transference learning. I guess it's the same task, so it's different, of course, but how similar, if you're familiar at all?
So I think that if I'm understanding the question correctly, like transfer learning is like I have two distributions, and I learn something on one distribution, and I want it to be accurate on the next distribution, right?
Mm-hmm.
In some ways, that's like a little different than what happens in performative prediction, because in transfer learning, you have like two arbitrary distributions. Here, all the distributions kind of arise from model deployment, right? These are sort of like you can think about them as like causal effects of deploying a classifier. So there's like a little bit more structure into how these distributions are related. And then this structure is like really important to say whether something will converge or not converge, or how tractable is it to deal with.
I also have one. So is there a way to deal with this other than just retraining the model? Like, is there a way to kind of get out ahead of the problem?
Yeah, that's a great question. So at the beginning, when we started this problem, we just thought like, well, what happens if you retrain? A different solution is to say like, I can maybe try to do a little bit of exploration, like deploy different classifiers and see how those affect the distribution. And using those, I can try to back out a model of like exactly how my classifier is affecting the distribution. And using that, you can do something that I think is in the spirit of what you just mentioned, where you build a model and try to solve a problem offline in the sense that it tries to kind of get ahead of what these effects are, right? You're sort of being a bit more proactive in terms of, anticipating the distribution shift rather than just like reacting to it at every time step. But yeah, that's a great question. So yes, with that, maybe I'll let Sadhika is up next, right?
Yes.
Yeah, if you want to share screen or get set up.
Okay, can everyone see this? Okay, great. So I'll be talking a little bit about some of the challenges that come up when we try to think about SGD from like a very rigorous theoretical standpoint. And so my goal is to just give some overarching ideas that inform this area of research and maybe not necessarily get into my results, which require maybe some more like formalism and things like that that aren't that exciting. Okay, so this is kind of a recap from the machine learning lecture, if you remember. So how do we get the S in SGD? What's going on? So we have this traditional algorithm, gradient descent. We're trying to find some minimizer of like our loss function. So we're trying to be as correct as possible or as less wrong as we possibly can. And so this is kind of the formula that we follow. And the eta here is our step size. So that's something we pick before we even start working. Okay, so here's like an easy way to think about this. So we're just moving these iterates in space. So we have like the iterate at kth time step and then at k+1 time. And we can kind of start to think of this as like a trajectory, right? So like we can follow this almost like a random walk through space, but it's not really random. So it's just a walk through space. So when we do stochastic gradient descent, we have a very similar formula, but this is more like computationally motivated, that we want to take the gradient or measure the gradient on only some subset of the data, because it's really expensive to like compute this full gradient every time we want to take a step. So now we're kind of in trouble. So we have this xk, this iterate here, but now when we want to go to the next one, depending on what batch or what examples we see and compute this gradient on, we could end up at like any of these points. So we no longer have this like nice, neat trajectory through space. As you can imagine, once you end up at say this point, you're going to go to like some other set. There's like another set of points that could be for xk+2. And so you can imagine how this kind of just like explodes and becomes really difficult to think about. So the exact path that we're going to take when we run SGD is going to depend on how we draw our examples. How do we compute this like sampled gradient? So maybe people can put it in the chat. What tool did we see in class that seems to sort of apply here? A more theoretical computer science tool. Maybe it's like hard to see in the stochastic gradient descent case, but in this gradient descent case, one of the tools we studied is like very obviously related. I also can't see the chat. Oh, maybe I can now. Okay, someone please put it in the chat, at least my like TA group, so I feel good about asking this question. Okay, it's fine. No one's gonna put it in the chat, it's fine. So I was thinking of MCMC, right? So, or more specifically like Markov chains. So we don't care about how we got to XK, we just use XK to compute our next step. So this kind of seems Markov chainy. The stochastic case also seems kind of like a Markov chain. Like we have some, we can think of like a transition matrix. Which of these points will we end up at? But we're moving in continuous space. So now our matrix, like we need some discretization of this, like we need to overlay a grid or something so we can think about these points as like reasonable transitions. So we won't be going too much into that view, but there are ways to extend those ideas to analyze SGD. So there's kind of a generalization mystery here. So remember, generalization is like we train on one data set that's like a sample of our total, like the population, all the examples in the world. And we want to do well on unseen data. So that's generalization. And so this is again gradient descent. Now, if we take our learning rate to 0, then what we get is like gradient flow. So hopefully you see how this differential equation kind of arises from this discrete update. So it's something like this. We see these red discrete points, and we're trying to understand what continuous trajectory do we take along here. Now, what does this have to do with generalization? It turns out that when we take these red discrete steps, we seem to for some reason, I'm saying experimentally, we're doing better than if we take these teeny tiny steps like along this. So what's up with that? What's going on there? And now when we think about SGD, which is what people are normally doing in practice, right? So remember we have this x0 and then we have no idea which of these x1s could arise, or ideally we'd want to consider these all under the same trajectory. So we're kind of like confused woman now, because we're kind of just like, okay, we have to follow these different trajectories. The number of trajectories is just like blowing up with the time steps that we take. It's just a lot to figure out. And SGD generalizes so much better than doing this like teeny tiny step thing over here. So we want to understand SGD with like some reasonable step size, like actually taking discrete steps. Why is that doing better? What properties does that kind of algorithm have that gradient descent or gradient flow don't have? So we need some kind of continuous trajectory, just like gradient flow, but we need some stochasticity in it because we need to account for all these possibilities for x1. And so this is kind of where stochastic differential equations come in. So I put the form of the equation here just so you get a sense for it. Like this is how x is changing over time, so our iterate. And then this is, we're just following the gradients. Everything is the same idea. But now we have this like additive noise term. And in particular, this WT is like white noise. It's like Gaussian noise. So this is just generally how people, one way that people are modeling a continuous trajectory with some stochastic element. So one thing that comes up a lot in SGD analysis is how close are two trajectories? This is a very difficult question to answer. So it's easy enough when you have something like this. You have x0, x1, x2. You have these like blue points. Maybe that's some other algorithm. Maybe that's like your approximation. And a simple attempt, right, would just be to take the maximum distance between any of these two iterates. That would be like in the easy case, we could do that. But now, of course, SGD is the hard case, right? So we have like many different options for what x1 can be. And then the other trajectory also has many options for what y1 can be. So now we're kind of confused. What can we do to say if these trajectories are close or not? One thing we can do is take the expectation. So this is one good way to kind of get around that. And another way is to introduce what's called a test function. So this brings this back to analysis and more pure analysis ideas, where maybe we don't care if we're close literally in like Euclidean space to the other trajectory. Maybe we just care if these two iterates get the same test performance, or if they have the same like gradient norm or something like that. So you can think of a test function as just like something that we actually care about with the iterates, not necessarily their values, but some other thing that we care about. Okay, so I thought I would also get into a little bit from the lens of mentorship. How is it that I ended up working on this? And so the first thing is like I kind of followed advisor and collaborator interests. This was not something I even knew existed going into grad school, and it's relatively new ideas and everything. So kind of just followed the lead of the people around me who were experienced and could help me with it. I learned a lot on the fly. Definitely didn't know anything about stochastic calculus and things like that. So I would encourage you to have like that open mind and be ready to learn like new topics if you want to explore different subfields. And bringing like a persistent and like rigorous attitude, which I think like math training, TCS training really gives you, goes a long way when approaching a new problem. I think being able to talk in formalisms and to logically see things through gives you a lot of like power when you're doing research. So yeah, that's all I wanted to say. Are there any questions? Okay, someone asked in the chat, how hard was learning new topics by yourself? I think it was hard, but it was very rewarding. There's something to be said. You learn a lot about yourself too, like what's the best way that you learn and digest topics, and it really sticks with you when you do it by yourself. But yes, it can be difficult. And like I said, following my advisor and like people in my group who have these interests help me kind of have people to talk to about like whatever I was stuck on or not getting. So that's also a good way to keep yourself accountable and have some support. Okay, I'll stop the share now.
All right, Chi-Ning, if you want to go ahead and get set up.
Okay, can you hear me?
Yes.
Yeah. Okay, also can you see the, oh, maybe I need to switch.
Yeah.
The slides looking good?
Yes. Yes.
Yeah, so hi everyone, I'm Chi-Ning. I'm a fourth year PhD student at Harvard, and I'm fortunate to be advised by Boaz. Yeah, and I thought this will be a very casual talk, so I didn't prepare too much on the details of my research. So it's just going to be a very overview talk on what I'm doing, what I'm interested in. Yeah, so maybe I'm going to start with this figure made by a friend, Kunal. Like it's a summary of the words appearing in the abstract of the paper I've written. So you can roughly get a sense like what topics I'm interested in. Yeah, but in general, my research is central around complexity theory. Especially, I'm very interested in circuit lower bounds, algebraic complexity, and streaming complexity, etc. And but the center from complexity theory, I branch out with two main other areas, to quantum computation and theoretical neuroscience. And potentially, I'm also interested in finding other connections. And in the rest of my talks, I'm going to focus on one example of the streaming complexity, which I've been working on a lot recently, and another very exciting direction, theoretical neuroscience. Okay, so what's streaming complexity? So we just see a streaming model by Johnny like an hour ago. Yeah, but here we focus on different sides. Yeah, more on the maybe complexity side, where Johnny focused a lot on the algorithmic side. And what do I mean by complexity side? It means that can we use the streaming model to study the unconditional lower bounds? Yeah, so what do I mean by unconditional lower bounds? So in a class, probably in the crypto class, we saw that like assuming one-way function, etc., lots of beautiful things happen. And this is kind of a very common thing in TCS, like people assume something and we get what we want. And this is also called as like conditional result. In particular, when we want to prove something is difficult, we usually need to assume an NP hardness or unique game hardness, etc. Yeah, in order to get what we want. Yeah, but and let me give a concrete example, which is max cut. Yeah, so for max cut, you probably learn in the undergrad algorithm course, like there's a 0.5 approximation algorithm. Yeah, in polynomial time. Although exactly solving max cut is NP hard, but we know there's a 0.5 approximation algorithm in polynomial time, even linear time, I believe. Yeah, and if you take an advanced algorithm course, you will probably see this Goldman-Williamson algorithm gives you 0.878 algorithm in polynomial time 2. But what about the hardness side? Yeah, unfortunately, to the best of knowledge today, the best NP hardness result is just 0.941, which is, you can see it is far away from the 0.78. Yeah, but a very exciting area like called unique M, it's like under another assumption called the unique M conjectures, people can show, okay, this 0.878 actually is the best you can hope for in polynomial time. Yeah, so you roughly can get a feeling like this kind of landscape is like you need to assume something and it's not so clear, it's not so unifying. Yeah, and through the streaming model, it turns out that we can prove unconditionally that you actually can, what's the best you can hope for. So let's take the max cut example again. Yeah, now imagine rather than receive the whole graph at a time, you actually receive edges by edges. So you have a limited spaces of computational resource, and you receive edge by edge. You cannot store every edge. And in the end, you want to output the size of the max cut. Yeah, so it turns out that in the past few years, people can show that the 0.5 trivial algorithm, you can implement it in log n space. But in order to beat this 0.5 trivial algorithm a little bit by epsilon, it requires linear space. Yeah, and this is not an accident. Yeah, like recent lots of follow-ups, including some of my recent work, we show that this can be done in many, many interesting other algorithms. Yeah, and this is a very rising sub-directions in streaming complexity, and there are more and more open problems to be explored. Like here, I name a few, like vertex cover, traveling salesman problem. Those are very, very not very well studied yet in the streaming model and could be of interest to prove some interesting unconditional results. Okay, so this is the overview of the streaming complexity I'm very interested in. Yeah, and another direction I'm quite interested in is called theoretical neuroscience. So this is kind of slightly away from CS and maybe out of our comfort zone. But by some accident, I got into this area a few years ago. Yeah, but originally it is maybe from a more biological motivation. But then I found there are actually more and more connections that maybe either our CS people can provide new insights to them, or we can also get inspired from them. Yeah, so the punchline is like maybe study neuroscience through the CS then can help us also get inspiration from the wisdom of nature. Yeah, so to give a very, very rough landscape on the big picture I have in mind is the following. So maybe on the left is the CS and on the right neuroscience. There are maybe totally two different words. Maybe there are two main approach you can hope for in doing research here. So the first one is maybe closer to neuroscience. It's like maybe we can investigate some interesting neuroscience phenomenon through algorithmic and complexity theoretic lens. Yeah, for example, one of the work I really like, I done like a few years ago, is that we study a spiking neural networks model in the neuroscience literature. Previously, they don't know how to prove like convergence result, etc. And by like using some cool optimization techniques, turns out we can prove very tight results there and also discover new properties there. Yeah, and in the meantime, one thing I found very interesting in neuroscience is that there are lots of biological constraints in the neural networks. For example, lots of things should be locally connected, or like lots of the connectivity should be non-negative. Yeah, and these things is not arbitrary. Yeah, sometimes there are algorithmic advantage or computational advantage there. So by using the CS lens, probably we can give more interpretation why those properties emerge and why they'll be interesting. Yeah, and another direction I think could be also of interest for CS people is to study more on the complexity or like the neuromorphic computation side. It's like if we try to implement artificial brain, yeah, what's the advantage we can get? Yeah, so the analogy maybe is like quantum computation. Yeah, can we find the shortest algorithm, which is like the first algorithm, quantum algorithm that people believe like a classical computer cannot do as well? Yeah, can we also find similar things in the neuroscience model? Yeah, So yeah, so this is the brief overview, of the research I'm interested in, and I'm happy to take questions.
So you said it was a happy accident or something that you got into this neuroscience. Could you just elaborate a little more? How did you find this area?
Oh, yeah, sure. Yeah, so I actually did my undergrads in Taiwan, and in Taiwan, there are not too many people doing TCS. Yeah, and I actually just learned some cool complexity theory in a class, and I want to do research there, but no one can advise me. Yeah, and the only closest person there is like doing cryptography, but at that time, I'm not so interested in cryptography. And my previous advisor there told me that, oh, there's his friend working IBM. They are interested in study the math underlying neural networks. Yeah, maybe I'll be interested. And I think, yeah, maybe that would be better because rather than working on some topics that I'm not so interested in, maybe I can learn from how my advisor like attacking new problems because those problems are also unfamiliar to him. Yeah, so that's like one motivation I had at that time, and I got into this and find it more and more interested. Yeah.
If there are no other questions, I'll go ahead and start my talk, I guess. All right, so I thought this work I had, which we called Sparks, would be a good topic for a lightning talk. Sparks stands for Succinct, Parallelizable, Arguments of Knowledge, and I'll briefly touch on what each of those words mean. And this is joint work with some collaborators, Naomi, Ilan, and my advisor, Rafael Paz. Okay. So the main application I want to think about today is that of delegating computation. And so this is a problem where you have some weak local computer, think like your laptop, who needs to perform some computation. Just represent it as some machine M that wants to compute some output given some input X. And the idea is that this computation might take a very long time to compute. So we'll call it T time. Think of T being like an hour, many steps for a computer to compute. And during this hour, I want to do other things. I want to be on Zoom. I want to do other things, and I don't want to use all my computational resources dedicated to this task. So what am I going to do? I'm going to actually just send this to some server like AWS to perform this task for me. So AWS comes back, gives me the answer, says M of X equals Y, but I don't know. I don't trust Amazon. I don't trust Jeff Bezos. Who knows what he's up to? So I ask for a proof in addition to the result of the computation. And this could be interactive, like we saw in the talk earlier today. And in fact, I could even ask for very general computations. Maybe AWS is computing over some large database. In order to capture these types of more general computations, it'll be useful to think not only capturing deterministic computations, but also sometimes non-deterministic computations. But for the sake of this talk, I just want you to think I have some task I want to solve, some computation I want to perform, and I'm just going to offload this to AWS to do it for me. And so what do I want from this scheme? Well, first, I want this to be convincing. So this is the argument of knowledge property. Really, it's something a little more complicated, but for now, just think of the aspect of it being convincing, which means that if they give me an output Y, that is the correct output of the computation, then I'll accept the proof. And if they give me something that's incorrect, I'll reject the proof. And then the next thing, to make this delegation scheme useful, I need that this verifier is more efficient than if I were to just do the computation myself. And that means that my running time should be much smaller than the original running time t. And furthermore, the communication should be smaller than t. So I shouldn't have to receive as many bits as long as the computation is. And these two properties kind of make it useful. And then because this is somewhat practical, historically we've said that the prover just needs to run in polynomial time in this time bound t. And so these three criteria are what makes this succinct, so the S from Spark. But this last point about the prover running in time polynomial in t is actually not quite so good, because the desired application is when t is very large. So this raises an issue of if the prover's overhead is even just a quadratic, so a relatively good polynomial, if our computation took like an hour to compute, if you square the number of operations that comes up with an hour on modern computers, this will be like 400 million years of computation. So this is just ridiculous. So what was known for tasks like these? So for many applications, because this is so important to kind of decrease the prover's running time, we know that we can have a prover that runs in essentially t with some small multiplicative overhead running time. So for all intents and purposes, we can think if we had an hour-long computation, we know how to do the computation as well as compute a proof that this is correct in a factor of 1,000 overhead in time. And so the new idea we have with this notion Sparks, so this P from Sparks is what we say is parallelizable. And the idea is that can we actually compute the computation and actually compute the proof completely in parallel to the computation? What I mean by this is we want, if there's some t time computation, the prover in total runs in parallel time t with some small overhead and is somehow using, say, something like 1,000, maybe a little more, processors on the side. But we still want the number of processors it needs to use to be much smaller than, say, t. So can we kind of have an hour-long computation that we delegate to some server and get a response in about an hour without wasting too many resources on the number of processors we need to buy from Amazon? So the main lemma we show in this work is actually kind of a generic transformation where we take some proof that has some multiplicative overhead, we massage it with some cryptography in the right setting, and we get this notion of Sparks. And what I want you to think of is that this is some way of trading off the multiplicative overhead of time for how long this computation could take. And we're trading that off for the number of processors we're using at a single instance. So instead of taking 1,000 hours, we're taking about an hour, but maybe using 10,000 processors. So that's the idea behind this transformation. And I'll just very briefly give a high level of kind of what might this look like? How is this even possible? And the big level picture is actually pretty straightforward. We're just going to break up the computation into different pieces. We're going to do some first part of the computation such that this interactive proof we're starting with will finish. We can finish computing this proof in some time t. And then after we finish this initial just computational part, we can kind of recursively apply this idea. So we do some number of steps, we compute a proof, and then in parallel, we'll compute some more of the computation and a proof. And at each time, we're just making sure that this proof will finish in some specified time. That's the entire time of the computation. And so the main contribution we show in this work is how do you actually use cryptography to break up this arbitrary computation to efficiently compute these proofs. Because when you break computation up like this, there are many issues that arise along the way. So yeah, that's this work on Sparks, where we have succinct proofs that are parallelizable and they're arguments of knowledge, where the prover can, in this delegation setting, can run in essentially the same amount of time as the original computation, but using very, very few processors. So yeah, I'll be happy to take any questions.
I don't know if you can see the chat, but somebody asked if AWS actually uses these.
No. So at least in the current time being, this is more of a proof of concept that something like this is possible. I don't know if, like, one of the main applications for something like this would be in the blockchain world, where they're doing a bunch of these kind of distributed proofs of some computation over some large history of the blockchain. But at the moment, there are no implementations, and to actually get it to a point of being useful in practice, there's a lot of work to do. But this is more of a proof of concept that even theoretically something like this is possible. But yeah, there are a lot of interesting questions of how do you make the crypto along the way efficient enough to actually make this implementable in practice?
Yes, and maybe I should say that, like, this is has a long history in crypto, where basically sometimes the road from someone proposing a theoretical idea and as a proof of concept until it gets implemented is very long, but it eventually gets there often. So some of the ideas of probabilistically checkable proofs and the ideas that underlie these kind of things, they were proposed in the early 90s. And I think there was many, there were over the 3 decades that have passed since then, there were many works that have managed to make it more and more practical and had to use a lot of new ideas. But now actually in the cryptocurrency domain, these kind of ideas are being used. So there is a long road from theory to practice, but eventually these things do have impact.
I have a sort of question about this area of research, I guess, and I'm just sort of forwarding a question from somebody who asked me a question at a conference once, which is like, do you know if anybody's working on verifying specifically that, like, say an ML algorithm is trained with a particular, like, objective function or something like this? Like, that seems like it would be really desirable, and I don't know if, yeah, that's a thing.
So I don't know the specifics. Like, usually from the theory side of things, we focus on NP computations or all of P computations. I do know I have seen a couple papers that are focused on, like, verifying specific, like, distributed computations that arise a lot in ML applications, but yeah, I'm not exactly familiar with the exact literature in that area. Anyways, if there are no more questions, I'll pass it over to Jess.
Thanks. Okay, can folks see my slides okay? Cool. All right, so yeah, I'm going to be talking a little bit about fully homomorphic encryption. Hopefully I can get across, like, a couple of key ideas because it's super cool. And thank you to Cody for already talking a little bit about delegating computation, because this is one of the main applications for FHE. And I'm going to give, like, just a sort of introduction to FHE, and then I'm going to, like, maybe have a slide talking about a thing I did with my advisor, Daniele, but this is mostly work done by like other people in the field, like, I don't know, Craig Gentry, or they're talking about the Learning with Errors crypto system, which is introduced by Oded Regev. So most of this is not me. Just want to put that up front. So what is fully homomorphic encryption? Let's, like, actually define this. So we'll have a scheme that's comprised of these 4 algorithms. So can folks see my cursor when I, like, wave it around the screen? Cool, thanks. So we have sort of 3 these, like, 3 subroutines or algorithms that are standard in, like, normal symmetric key or public key encryption, we have some sort of key generation process. We have an algorithm for actually encrypting messages, and then an algorithm for recovering them by decrypting. And fully homomorphic encryption is special in that it comes equipped with this fancy additional routine that we'll call eval. And what eval is going to let you do is perform meaningful computation on data while it's encrypted. So what I mean is I can perform like eval of your favorite function f on a particular ciphertext, give it to you, and then when you decrypt it, you'll recover not the original encrypted value, let's call that m, but the value f of m, the function that you had me evaluate. So I can evaluate this function without actually knowing m, like your secret data at any point. So here's sort of like, so this is maybe it's sort of spelled out. So this is, I guess like the type of eval, right? It should take a function. It can take one or more ciphertexts, and it should output a valid encryption of the function applied to the values that those ciphertexts were encrypting. So why would we want to do this, aside from it just being pretty cool? So we can imagine like here we have Alice. Alice runs a like profitable lemonade stand and maybe wants to perform some data analytics to figure out where she should expand her lemonade business, but she has this little tiny hamster-sized computer, and so she can't possibly perform the computation that's necessary to figure out where to like optimally place her stand. So she's going to delegate this to some sort of cloud computation as a service provider. So the thing is, like, Alice doesn't want to reveal like any of her trade secrets or any of her customers' data because Alice is a responsible business owner. So she doesn't want to actually like send that data in the clear to the cloud. So she's going to encrypt it first. She's going to send an encryption of like, let's say her entire customer database and to the cloud, along with the functionality, some sort of specification of the function that she wants to compute on her data. The cloud will do this for her and return to her ciphertext or ciphertexts, encrypting the result of that computation. And again, the critical piece here is that at no point has the cloud actually seen Alice's customer data in the clear, right? So they just got ciphertexts, but they were still able, using homomorphic encryption, to perform this functionality f, or evaluate f on the customer data while encrypted. So there, Alice gets back the ciphertext, and then the correctness property of fully homomorphic encryption demands that when Alice decrypts the resulting ciphertext, she actually gets back the evaluation of the function f on her customer data. Great, so this is what this whole talk is about. So do we have any questions now? I'm guessing things in the chat, are still about the cat. Cool. All right. So I will keep on talking a little bit about how we build FHE. I unfortunately can't get into this in a lightning talk in too much detail. So I'm going to blaze through some math and then try to get right to a TikTok video that I think is surprisingly illustrative for one of the main technical obstacles in building FHE. So an example I'll sort of introduce is what if we just care about not performing arbitrary functionality, but we just care about being able to add ciphertexts homomorphically, like, without having to decrypt. And there's a crypto system called Learning with Errors, again introduced by Oded Regev back in like the early mid-2000s. And it looks a little something like this. The key property here, like, you don't have to, you can stare at this math for a while if you like. You don't need to internalize it. I think the important property that we're going to care about the most here is that this has like a nice linear property. So you can just sort of think of this crypto system as being linear. So to encrypt a message M under a key S, we're just imagine M being a bit and S is a vector of integers mod Q of n dimensions. To encrypt this message, we're just going to sample another random vector from the integers mod Q in n dimensions, take the inner product with our key, use this as a kind of masking value, sample an error term E from a discrete Gaussian, which is just a Gaussian over the integers, specifically mod Q here. So we're going to sample a little bit, a small error term, and add that onto our mask. And we'll use this as essentially like a pseudo-random mask for our message. It's worth noting here that I'm not using this as a mask for the message directly, I'm encoding the message by multiplying it by Q/2. And I have a little cartoon in a second that should maybe make it clear why we want to do that. And then to decrypt, just so you can see what the decryption operation looks like, we're just going to undo this process. We're going to subtract off the mask from the second component of our ciphertext. We're going to undo the scaling factor. We don't know what E is, right? So we're decrypting. We weren't there for encryption, so we don't know what the value of E is. But because E is presumably small, since it came from this Gaussian, when we undo the scaling, E will get smaller. And so we're just going to round. And then we can show with high probability that from concentration bounds on the Gaussian, that this will give us the correct message so long as the error term wasn't larger than Q/4. And this is sort of why we want to do this encoding by multiplying by Q/2. That gives us some wiggle room. We're able to decode these messages if we sort of puff up our message. So the idea here is you can imagine the integers mod Q as being like laid out on this circle. And after we subtract off the masking term, inner product, our secret key, if we encrypted a 0, we're going to have a value somewhere in this region. And if we encrypted a 1, we'll have a value somewhere in this region, again with high probability. And so you can essentially just say, okay, what part of the circle am I in? And then decrypt to 0, run accordingly. Cool. So again, it's not super important that you feel like you're really comfortable with LWE at this point. The important thing to see here is that one, it's linear, and two, there's error. And the error is going to be really important to security, but it's also going to pose a problem for homomorphic computation. So to see that we can perform homomorphic addition with an LWE crypto system, let's just look at what happens if we add 2 ciphertexts, right? So ciphertext 1, right, was just this random vector, the inner product, error term, and then the encoded message. Same thing for the second one. And you can see that when we add these together, again, because of this like linearity property of LWE, what we're going to get is a valid ciphertext just with a different random vector A and with a different error term. So this is a valid ciphertext encrypting M0 and M1, but the error term is larger, right? And we said that we can only actually decrypt and get back the message, like the correct message, if our error is less than Q/4. So we're going to have some like limited number of additions that we can do before it's just like garbage. We can't actually decrypt messages anymore. So how do we deal with this, right? How can we manage error? And that's where this idea called bootstrapping comes in. I think it was like introduced by Craig Gentry in 2009, and like a super cool seminal result that sort of, I don't know, like reinvigorated the field of research of fully homomorphic encryption. And the idea is, what if we have a crypto system that so we can perform a certain number of operations in this crypto system homomorphically, but then once we exceed our error budget, decryption starts failing. But we have some budget for error. We can perform a few operations. So what if our error budget was enough to let us perform decryption homomorphically? Okay, so I'm going to go through a picture of what this means, and then we'll get to the TikTok video, assuming we have time. Okay, I'll be quick. So again, this is our decryption function here. So sort of one of the main pieces is that we want to compute this inner product. When we have a linear encryption system, so presumably we can do this. But let's imagine we have like something that's even stronger than LWE that also lets us perform all these other steps of decryption homomorphically within the error budget of a crypto system. Okay, so here are 2 ciphertexts. Let's say we want to add. We have one LWE ciphertext with small error encrypting 0, one with small error encrypting 1. We add them together and we get a ciphertext encrypting 1, but with larger error, right? So we want to get rid of this error somehow so that we can continue performing computation. And the idea here is that we're going to put this ciphertext inside another ciphertext. And then we can start adding encryptions of our key material, essentially like the terms of this inner product. We can add them one by one homomorphically because our LWE plus homomorphic encryption system enables this. And this allows us to compute the inner product term or portion of decryption. Again, I haven't given you an idea of how we might be able to do this, But our LWE plus encryption system also allows us to homomorphically round, which lets us, sort of get rid of the rest of that error. And then it also gives us an extraction procedure, which lets us convert an LWE plus ciphertext, which I've drawn to be larger to emphasize the fact that they are bulky and computationally expensive, and extract a nice lightweight LWE ciphertext that we can resume operating on. And so the error that we have from this resulting LWE ciphertext is going to be roughly the error that we introduced while we were performing decryption. So we've now reduced the error to something lower, and we can start this whole process over again. So again, this is very confusing, I think, the first time you see it. And so this is where I sort of want to get to the TikTok video. I don't know if I have to like explicitly share this, but I'm going to show a video of somebody changing their shirt without removing their shirt. Okay, so this is, I want you to think of putting a shirt on as like encrypting your torso and then removing a shirt as decrypting, okay? And the idea is you have a shirt, you've been wearing it for like a while, it's gotten dirty and nasty, it's not really like serving the purpose of a shirt anymore, and so you want to, but you're in public, you have a second shirt, you want to change into that, so you have a nice clean shirt again, but you don't want to actually reveal your torso at any point because this is sensitive information you'd prefer not to share. So can people see the TikTok? Cool. Okay. Oh no, I should stop this looping. Okay, so that's sort of like, that's bootstrapping in a nutshell, I think. And okay, so
that's a great
like
metaphor.
Sort of like...
I'm going to use it when I teach crypto next time.
Nice. Yeah, I've never actually been able to give a talk before where I've been able to use this analogy. I've tried, and it's just always been like either vaguely inappropriate or there hasn't been enough time to sneak it in. So I appreciate having this opportunity, because I feel like it's a really useful analogy. But
yeah, I mean, when in my lecture notes, I try to use this analogy of trying to kind of put things in a Ziploc bag that deteriorates. So you have to kind of move to a different Ziploc bag while you. But it's kind of yeah, I like this this analogy better.
With the negative 1 minute that I have left, I sort of want to say like what work I've done on FHE. And the work that I've done is explicitly on speeding up this bootstrapping process. So it's sort of like integral to be able to really build fully homomorphic encryption, but it's really slow, right? Just like the video we just saw was like much slower than if you were just on your own changing a shirt, right? You could probably pull it off faster. So Daniela and I showed that we maybe didn't speed up the bootstrapping of like a single ciphertext, but we showed that you can actually get away with bootstrapping a whole bunch of ciphertexts for just the cost of essentially the cost of bootstrapping a single one. So you can think like, oh, if you had n ciphertexts, maybe it costs like n squared operations to bootstrap them before, and we were able to bring that down to something like n to the 1 plus epsilon. So it's faster, but still not fast enough to be practical. So if you're interested in this, people are like very interested, like both in academia and also apparently in industry. I'll be talking to Samsung later about like trying to help them implement FHE for some of their products. So people are interested in this, but it's still like very much in the realm of theoretical and not quite practical, but it's getting closer every year. So maybe you can help us. Thank you for your time.
All right, thanks again to all the speakers. If there are any additional questions, we can hang around for a little bit. Otherwise, it's after whatever the end of this schedule is for you. So feel free to drop off But yeah, thanks everyone for coming and listening to our lightning talks.
Thank you for organizing.